Hi, my name is Evgeny Garnov. I am a solution architect from Conformiq Software. I have a pleasure to present you first part of our Getting Started with Conformiq video series. This series will show you the whole process of testing with Conformiq. This series will consist of 5 parts where we will focus on different aspects of automated test design with Conformiq. Based on the specification of system under test, we create a system model which represents a real system under test behavior. Then we configure test generation controls which will guide test generation process to generate test cases exactly what we need. When both model and test generation controls are loaded to Conformiq, we push one button and Conformiq generates test suite automatically. And it includes human readable tests for review, execution test scripts, test documentation, traceability metrics, and test coverage report. In this part we will consider creation of a model, which consists of 3 building blocks: system block, UML state machine diagrams, and Java-like action language part. In all getting started videos, our system under test is a simple calculator. This is just an example. Watch one of our demos to see other, more complex examples. Let's start from reviewing our system under test or calculator specification. Based on the specifications, we will create a model representing a specification that can be read by computer program or Conformiq Designer. Our calculator has a conventional interface and logic. Calculator supports 4 basic arithmetic operations: addition, subtraction, multiplication, and division. Keep in mind that Conformiq Designer automates black box test design. In other words, we test that outputs of a program, given certain inputs, conform the functional specification of the program. Inputs of the calculator will be keys, which user can type, digits and operation keys, and the output is a display showing the numbers. Now let's adopt this knowledge and create a model for this calculator with Conformiq Designer. This is a Conformiq Designer window. First I will create a new project. I name it calculator. Next we select to deploy default model files. This way Conformiq Designer generates for us initial templates files to work with. We name the main class of the project as calculator. Now our Conformiq project has been populated and it has several entities: DC1, use cases and model folder. I will skip DC1 and use cases for now, and let's talk about model folder. This folder contains the source code of our model, and Conformiq deployed automatically 4 files here. File main.cqa is an entry point to our model. It contains definition of main function. The main function is an entry point to our specification of the behavior to be tested. The code generated by Conformiq creates first an instance of the model component calculator, and then it starts the component. The Conformiq project wizard has generated code which creates and starts one model component. Typically, you don't need to modify these files for single components projects. For an example of working with multiple components, please refer to Conformiq Designer end-to-end example model. You can find this and other example models via your File menu. The second deployed file is system.block.cqa file. It describes an external interface of system under test. That model which we create is abstract with respect to environment. Conformiq Designer does not provide means for reading keyboard, opening files or internet connections. Instead of this, model communicates with external environment by means of external ports. External ports might be inbound or outbound, and declared accordingly using keyword inbound and outbound. External ports are unidirectional, and inbound states for from tester to system under test or keyboard for calculator, and outbound states for system under test to tester or display for calculator. Ports are always declared inside a system block which initiated by system keyword. Typically, we start building our model by modifying the system block generated by Conformiq Project Wizard according to our specification. And let's go back to our user interface chapter of our specification and identify external interfaces for our system as a black box. The inbound interface here is key part, with three types of inputs: number, operation, and equals. Similarly, the outbound interface is display with one type of output. Let's visualize it. We have our calculator here, and here is inbound port key part, and outbound port is display. We have identified external interfaces with two ports, and we can draw our calculator as a black box now. All the information needed for creating a system block is on the screen. Let's rewrite it using Conformiq syntax. For inbound port key part, we identified three types of inputs: number, operation, and equals. Each of these inputs must correspond to record type definitions available in Conformiq. Below you can see three record definitions: number, operation, and equal. Records carry the actual data between system under test and environment. Number carries the actual float number. Operation carries the operation type. And equals carries the signal to initiate a calculation and display result. For outbound port display, we identify one type of output. It corresponds to mentioned previously record definition number. Please notice that we specify only the message structure. The actual message content will be generated by Conformiq using pure mathematical algorithm. Now I will paste the system block and type definitions into our project. Let's consider the third deployed file, calculator XMI. This is Conformiq Modeler, the UML state machine editor shipped with Conformiq. We use state machine to define the actual behavior to be tested. Now you can see a state machine which was generated by the Conformiq project wizard. It is very simple, however, contains a minimal number of elements needed for successful loading of generated model files. The state machine has an initial state, a state 1, and a transition. Additionally, it has a note element, where you can add your comments about the behavior model by state machine. Notes can be used for model documentations and are ignored during test generation process. Here we will create state machine representing our calculator, and I will do it step by step with you. I recommend you to keep your state machine elements aligned with respect to grid from the beginning, and I will do some simple alignments now. I will paste our system block definition into the node in this example to help us remember our previous system block definition. Let's now specify the system operation to be tested. An addition of two numbers. The first thing that happens from the calculator point of view is that it waits for the user to enter the first argument, then it waits for the operator, and so on. So I rename a state to wait for first argument to reflect our specification. Now I add another state using toolbar element and name it wait for operation. Now let's connect our states by transition elements from toolbar. According to our specification, the transition between these two states is triggered by receiving the input record number through port key part. Let's reflect it in our model. In UML, the part of state transition body before the square parenthesis is called trigger. When using Conformiq, we specify here port name and input type to be received by the system separated by column. Note that by using the type number we specify here not a specific number to be entered, but any number. And as we will see later, Conformiq will compute as part of automated test design a suitable number for us during test generation. According to the specification, upon reception of the number, calculator must display it. I reflected again this fact in our state machine. The part of code after the slash is called in UML an action. The action part of the code is executed when transition is triggered or activated. This is in this case. Only after the user has entered a number on the keypad it is displayed. MSG is a construct that enables us to access the message received in the transition trigger block. It is visible only inside the body of the transition. In the send statement we specify first the port to which the message is to be sent, in our case the display, and the message, in this case the number received from the keypad. Let's add the next step, state and transition. This transition is triggered by the input type operation, which carries information about the operation button selected by the person operating the calculator. The transition body is similar, but according to the specification the first argument must be again displayed after the operation button is pushed. We have come up with a problem. We need to use the data received on previous transition, but as we stated earlier the variable MSG is visible no longer than in one transition. In order to overcome this problem, I introduce the variable a to save the received value. Now I will rewrite an action part of a new transition and use this new variable. Here we have created a variable of type number, then we initialize its field value and we send it to the display port. This demonstrates how we can use inputs received on previous steps. Next I add another state, wait for equal. The transition is triggered again by an input of type number and we store its content in the local variable b and display it immediately. On reception of equal record, our state machine reaches its final state and I add a final state. Please notice that life cycle of a calculator never ends. But according to the specification, for testing purposes, we want functionality to come to an end at this point. So, final state is the end of our modeled system operation and generated tests. What should our calculator display in this action block? The result to be displayed actually depends on the operation chosen by the user previously. Again, behavior of our system depends on messages received on previous steps. Let's store our operation type in a local variable. Let's store our operation type in a variable. Now we can create different paths of behavior based on the value stored in the operation variable. The part of transition body in a square parenthesis is a guard. A transition can be triggered only if the guard is evaluated to true. I will add our condition as a guard here. We send output with the result of the addition operation to the display. And now I will implement in the same way the other operations: subtraction, multiplication and division. Please notice that state machine may have several final states, but only one initial state. Since we have implemented all the functionality, let's align our state machine. And now I will zoom out our model. And this is our functionality from bird eye view. After we have finished our system block and specified the system operation to be tested, let's try to load our model to computation server using load button. Every time when Conformiq loads a model, it checks the correctness of its syntax and reports compilation errors if there are any. We have plenty of errors. Errors are related to undeclared variables a, b and operation. We use these variables, but we never declared them. If you want to declare a variable visible within several transitions of one state machine, you have to declare them inside a class representing your state machine. This class definition was generated by Conformiq project wizard in the file calculator.cqa. This is the fourth and the last file which was generated by the wizard. Please notice that the class representing a state machine must have exactly the same name as a state machine calculator. I will now add the required variable declarations here. Now let's try to load our model again. Now let's try to load our model again. The model was successfully loaded to computational server. It means that it doesn't have any syntactical or other compilation error. And the next step is to generate test cases. We have successfully generated 4 test cases. We will review these test cases in next videos of our series. And let me point out that Conformiq detected a model defect, division by 0. This is due to incompleteness of the specification. specification does not mention a special case of division by zero. And in next videos I will show you how Conformiq help us to investigate the incompleteness of the specification during test generation process. In this video we have considered creation of a first model from the specification. We reviewed Conformiq project wizard and files generated by its main system block, state machine and class files. We considered a concept of system block, external ports and records. We considered the main concept of UML state machine diagrams like states and transitions, guards and triggers.